I'm Tycho Andersen, and I is this feed? Is that okay? Do I have too much hair? Is that what the problem is? I currently work for Cisco, and I've been working on this patch series for the kernel for a while about forwarding syscalls to user space. And I guess the question is, why would you ever want to do this? And because then you can load kernel modules from inside containers. And I hope that scares everyone, because the container should probably not be able to inject arbitrary code into the kernel. But if you know sort of how containers work and how kernel modules work, you can see why this might be useful. So in particular, the init module syscall looks like this. So you hand it some module blob that's a memory area and length and the module arguments. And then the module blob's actually a special kind of ELF binary, and so the kernel parses that and does some other things and then loads the code if it looks valid. And so inside of a container, of course, you don't want to be able to insert these modules, but if you're running code that doesn't know that it's going to run in a container, for example, if you work at a large company who has lots of legacy code like Cisco, you may be interested in running that code in a container, but without teaching that code about how it looks, and it may be interested in inserting kernel modules. And so while you don't want to allow this in a general case, if you parse the module blob and you see, okay, this is okay, or another instance is if you are a container which was built against a different kernel, you try and do a mod probe of a particular module that you think you want, but the container, the host actually knows, oh, actually he doesn't want this one, he wants some other one, and I have a version of that that's built against and linked against the right kernel. So I can parse this module blob, figure out which one is the right one, and then load the right module. So that's, it sounds scary initially, but actually maybe it's not so bad. There's other things that might sound scary. So Christian just gave this whole talk about user namespaces and mount and stuff. So generally you can't mount stuff in a user namespace. And the reason is the kernel has this thing, Christian also talked about super blocks and stuff. But the important part is this red line here, which basically says only real root can do these kinds of mounts, unless it has some other flags, this fs user and s mount. So there's some exceptions, but generally only real root can do mounts. So the question is, what if we wanted to allow this anyway? It's like, for example, you may be mounting some device which you know nobody's ever written to before because you just got it fresh from the cloud, from your container orchestrator or whatever. You may want to allow the container to mount this device as a volume for storage or whatever. So the question is, how would you do this? So you'd start in the container all the way on the left-hand side. It would call the mount. It goes into the kernel. Then there would be some magic. It would forward it to the user space, which could then decide whether the request was valid, set an S to the container's namespace, do the actual mount, and then tell the kernel, okay, now you can tell this task that the mount succeeded, even though we did this magic thing and we didn't actually run the mount code from the VFS in the kernel. So how can you do that? And the first way is you can use ptrace. So you can ptrace attach to a task, and then you can step through every syscall forever until you realize, oh, this is a mount syscall, and then you can do the thing, but then you have to step through every syscall because ptrace syscall stops every time a syscall enters or exits. So as you might imagine, this is quite slow because you're trapping to user space on every single syscall, which you don't want to do. You only want to do on certain syscalls. So actually, the seccomp people thought about this, and they were like, well, hey, let's implement a special return code. So this is a really small filter in BPF assembly, so it's not super readable, but the important part is this red piece here. Basically, this filter says, hey, if this matches the mount syscall, if the syscall number is the same, then return this special seccomp ret trace option. And so what that does is, if somebody happens to be ptrace attached to you and has this special seccomp ptrace option set, they will get a signal when their tracee hits this condition. So that means basically in the kernel you can decide what syscalls to look at, so you don't have to go back to user space. So you can implement this a little bit more efficiently. But the thing is that this basically only allows you to say this still requires you to be ptrace attached to the task. And so the question is, well then how do you debug something that's using this ptrace? And you basically have to use the Feynman algorithm, which he's a great physicist who was famous for giving this algorithm of write it down, think really hard, and write down the solution. The problem is that if you're ptrace attached to it, nobody can debug it because they themselves can't ptrace to it. So if you're in this container and you're trying to debug around, but the container orchestrator has ptraced the thing to do this crazy syscall manipulation, you can't use strace inside the container. And so that's a problem. strace is a well understood debugging tool used by lots of developers, so you want that to work. So there, this is pretty much almost all the way there, this seccomp thing, except for the requirement of ptrace. So this patch series that I've been working on is to basically get rid of that. So we introduce a new seccomp return code that instead of giving a signal so that the ptracer can receive the signal and then look at the task, we forward all this stuff to a file descriptor, and then you can listen on the file descriptor and get events about this. So what does the actual API for this look like? So on the left-hand side here, you can see what the structures look like. So a notification will have a length, which is basically the length of the structure. This is so we can future-proof the kernel API. So if we add something in the future, that we can extend the structure and the kernel won't freak out on us. An ID, this is a unique ID for this particular filter. So it's just basically a way to eliminate some race conditions, which I'll talk about later. That's what we use the ID for. The PID, this is the PID that caused the thing to be sent. Then we have a flag here that indicates if there was a signal or if this trap was a result of a signal. So there's a little bit of an implementation detail here, which I can talk about later about what happens when signals happen. And then the struct seccomp data, and this is the same seccomp data that you can inspect normally that everybody gets, that you would see in the kernel if you're using BPF in the kernel with seccomp. And then the response, you have to pass this unique ID. Again, this is how we avoid race conditions. Then there's error and val. These are taken directly. If you've ever written in kernel seccomp filter, there's two return codes, two return values. One is this error and one is this value. And it turns out the way this works in the kernel is a little bit funny. So the error code is used if the error code is used if it's non-zero. Otherwise, we fall back to value. And the reason that there's two of them, I didn't understand this, so I went and looked. And it turns out there are some architectures which have two return registers, one for error codes and one for values. So for like every normal person who's using ARM and AMD64, this is just sort of an artifact. But there are architectures where you can return two things from a system call, so that's why this is there. So anyway, you can set an error condition or a value that you want the system call to return, and then you can also pass an FD. So for example, system calls like socket return a file descriptor that is the socket that you opened, or the open system call returns a file descriptor that is the thing that you opened. So what this is it basically says, hey, I'm the tracer. I did some stuff, I produced this file descriptor, and now I want to send it to the task. And so this basically makes the kernel take this file descriptor and put it in the task, and says, just return whatever that value is. So it will open a new file descriptor in the table of the tracee and install this file descriptor and then return whatever that value is. Now, actually, this API hasn't been merged yet, and I think we're thinking about changing how this works, so don't quote me on this. This won't be perhaps what goes in for the final version, but if you have input, there's a link later in the slides. Come reply and tell me what I should really do. So those are kind of the inputs and outputs. And then on the right, you see how you interact with it. So there's basically two ioctls. One is to receive a notification. Then you can do whatever the stuff you want. Then you return the notification by sending another ioctl. And so, Okay, so then the question is, we're using this file descriptor in the ioctl. How do we get one of those? So there's two ways to do this, and the reason there's two ways is that it's a little bit, it's kind of useful to have both. So the first one is when you install the setcomp filter, you can say, hey, give me one of the special event file descriptors back from installing this filter. So you might do this if you're going to install this filter and then exec a bunch of stuff that you want to handle stuff with. Or you can, as the comment says here, you could install this file descriptor and then send message that file descriptor to a server who would then handle all of your stuff for you according to whatever policy it thinks. The problem with this is actually that send message. So the problem is if your setcomp filter itself blocks send message, then you can never get this file descriptor out. And so you can only do this for child processes, which is not itself so useful. So then there's our old friend ptrace. I've implemented another way where you basically just attach to the task, say, give me a file descriptor for that particular filter. Then you can detach. The task can go on its merry way, but you can still do the send and receive. So there's two ways to get this. And they're both kind of useful in different scenarios. This one I think is much simpler to do because you don't have to deal with ptrace, but it sort of has limited utility in specific use cases. Okay, so then there's this sort of question of what happens in do stuff. The problem here is that this is kind of a minefield. In particular, setcomp, the struct setcomp data, I didn't give all the members here, but it doesn't give any contents of any memory. The only thing it gives is the register contents. And the reason for that is if there's another task who has write access to that same memory, there's a time of check, time of use issue where the setcomp layer may look at the system call and decide, oh yeah, these arguments all look reasonable. And then some other task can come in from the side after the setcomp stuff has said okay, but before it actually hits the VFS or whatever the actual kernel processing is happening, and it may change those arguments. And so then there's bad things that happen. So you have to be very careful. There's a couple of these issues that we'll talk about here. So it doesn't, I guess I just talked about the first one. It doesn't include memory contents because of the time of check, time of use issue. There's also this race condition, and this is why we have the ID in this structure. The second point, if the PID makes a syscall, the notification gets sent to userspace, and then the task immediately dies because it gets killed by the out-of-memory killer or any one of 100 other reasons. You need to make sure that if some other task starts up with the exact same PID, that you don't have this situation where you're actually responding to system call results for the wrong task. So there may be some task that was in user space that had this PID and it did this thing, and now it starts up one that's actually root, and now you're sending weird syscall results to root or whatever. So there's an issue here. So there's actually a check where you should open all of the resources that you're interested in using, and then there's a call on the ioctl for the file descriptor. You can basically say, is this ID still valid? Meaning, does this correspond to the same process ID? And that's what the ID gives us is security against this race condition. And the third one is you basically have the same problem. If there's two tasks, you have the same problem that I described before, where there's two tasks and they can write to the same memory. If you copy stuff out of the memory for the task, but you check it before you've copied everything, you might make a decision about policy that's incomplete because you don't have the whole picture. So basically, you can, and I have some code that does this in the patch series, but you can copy that information out with procpid mem, but you need to be very careful to only apply the policy after you've read all of the task's state. So here's just a simple example. If I was going to implement do stuff for mount, suppose I was only going to allow bind mounts, which is kind of, you can already do this with your user namespaces, but just for the sake of argument, it's easy to understand. So the first thing I would do is the third argument for the mount syscall is are the flags. So the first thing I would do is see, is this a bind mount or not? If not, then I'll return 0. I return 0 because reasons. Just because this is a successful call. What it's going to do is generate an error condition. So that's the reason for return. Anyway. So then I go through, and here's where I avoid the first time of check time of use issue. So I open the procpid mem for the particular task that triggered the notification, and then I check with this special ioctl that says, hey, is this still valid? Because otherwise I'm reading some other task memory, and who knows what that is, or I don't want to be doing that. And then the second time of check time of use issue is when I read the arguments. So I'm going to read the source for the bind mount and the target for the bind mount to apply some policy. I need to read both of them before I apply policy. So here's me, and I seek to so the first argument of mount is the source. So I seek there, read it, and then the second argument is the target, seek there, read it, and then this bottom code here, this is how, so I've read both of the arguments into my local memory in my task, so nobody can edit it or anything. So now I know there's no time of check time of use, because this is the thing that they want me to apply policy to. And then I apply my policy, which is, in this case, a dumb policy where I only allow bind mounts from /temp. So there's, I encourage you to come look at this. Here's a link to the kernel. I think this is version 6. I think it's pretty close. We have a few issues that people pointed out with this one that I'll post for the next version, but I would encourage all of you to come give me feedback and tell me why I'm wrong. There's also in the series this code I pulled out of an example that is just a sample of how to use this API. If you look at some of the tests, I'm doing crazy things in the tests, like returning file descriptors from the getpid syscall, and so there's just all sorts of heresy happening. So there's a lot of really weird stuff that you can do here. I suspect I'm not creative enough to do all of the cool stuff that is being done, but there's a lot of smart people here, so come tell me what would be cool or what else we need in the API. Just to talk a little bit about I've mostly talked about how you would use this. There's a number of implementation issues. The biggest one in my mind, and actually the one that I've received the least comments on, which is sort of frightening, is the synchronization. So as you might imagine, because you're synchronizing across tasks, this becomes a little bit hairy. So, this task is trying to inject a file descriptor into this task's file descriptor table, so everything needs to be in the right state of locks and stuff like that. So I think I've gotten it all right, but there would definitely I would be interested in some review there. Another issue early on, the ID was not unique, and so we basically just changed this to a U64 and did some math. It turns out if you make something ridiculous like 1 million system calls a second, U64 gives you like 578 years of 1 million system calls per nanosecond or something before it rolls over. So that's how we get uniqueness, is we just cheat. But if we're all still here using this same code in 578 years, there are a lot of other problems. So that's another issue. Jan Horn pointed out that the reason I'm using ioctl, originally I had this designed with read and write, but if there's some binary that's an equivalent of a setuid cat, you can trick things into manipulating setuid binaries themselves and cause other problems. There's a whole thread on that, so I think that's V5 maybe, so go check that out if you're interested. We also switch the FDC groups much as SCM writes does. The behavior is sort of intended to be the same as if you just sort of sent this file descriptor via SCM writes. So those are some implementation issues. So here's another link, I guess. Like I say, the userspace API is mostly done. There's some optimizations for structure size, I think, in this revision, and some other minor things, minor fixes, but it's mostly reasonable. I had a demo, but I'm here. My laptop's over there. I think it's a Windows laptop too, so no demo today, but I think we're running late, so thank you. And I'll be happy to take any questions anybody has. Please don't throw tomatoes. Yes?
Well, we still have a really small time gap for a really short question.
Yeah, I think there was one here. I can just repeat it if you want.
Yeah, I see.
Yep.
I see the hand. I know him.
Why do you
Oh.
why do you using syscall and not mechanism like kprobus, for example? For example, pair of tries is using kprobus. Is there some requirement or?
Not, I mean, really the reason is because they already had some functionality that was very close to this with the ptrace, setcomp trace. It's really just sort of a different extension of that. But there's, I mean, you're right that it easily could be based on kprobes or something else. Really, it's just they already have this struct setcomp data, and they've already thought about a lot of these issues. So it was sort of easier to build on that. But there's no, I mean, no real reason. Other questions?
Okay. So once again, thank you
Yep.
for our speaker.